I'm Chean Hao, a computer science student from Monash University, and this is a video recorded for my FIT3183 Malicious AI Unit third assignment. For this unit, I am implementing a deepfake detector, MesoNet, in an attempt to modify and improve it in some fashion. In this table of contents page, there are three items outlined for the following slides: MesoNet, CMAES optimizer, and PSO. CMAES and PSO are both optimizers that I tried to replace Adam with and would be explained further in the presentation. But for now, let's talk about MesoNet. The story of MesoNet began when its authors scrolled through various political groups on Facebook as a challenge. After the horrible incident, they keenly understood the need for a deepfake detector that works on the average Joe's computer. As such, MesoNet was born. A compact deepfake detector that specializes in detecting deepfakes generated from deepfake and face-to-face, two of the most widely used deepfake generation methods. The detector was made for videos that are highly compressed through endless cycles of reposting on social media, namely H.264 video encodings of the levels 0, 23, and 40. 0 being lossless compression, 23 being light compression, and 40 being highly compressed videos. The main idea behind MesoNet that separates from the rest is that it is meant to act as a low computational cost option for battling the swarm of deepfake videos on social media. Of course, most deepfake detectors out there are designed with the idea of balancing out computational costs, accuracy, generalization, and robustness. MesoNet over here simply zeroes into the computational cost, accuracy, and robustness part, sacrificing generalization. The limited variety of the dataset allows MesoNet to optimize itself to the point where it will be accurate on deepfake and face-to-face datasets, while only needing a few hours of optimization to reach good scores of more than 95% accuracy on a standard consumer-grade computer. Keep in mind that this model was made in 2018, where the average person's computer will probably only have 4 gigabytes of RAM. To explain further about MesoNet, there are two different network architectures presented within, both implemented with Keras, a Python API. One of them is Meso-4, where the input goes through 4 convolution layers and one densely connected layer at the end. Each convolution layer has a different number of filter and filter sizes, starting off with 8 filters and a 3x3 filter size, to 16 filters with a 5x5 filter size. ReLU activation functions were used in this case to introduce non-linearities, while batch normalization helps in regularizing the output and preventing the vanishing gradient effect. For the last densely connected layer, dropout was used as a way of regularization and robustness improvement. The second network architecture is Meso-Inception-4. Meso-Inception-4 possesses a similar structure to Meso-4, but differs in the first two layers being inception layers instead of convolution layers. Inception layers are a bunch of convolution layers stacked on top of each other, with each layer having different kernel shapes. The dilated convolutions are used to prevent high semantics. This inception layer is mainly used to further deal with multi-scale information, allowing the model to better analyze images from different levels of details and resolutions. Now, with MesoNet's architecture explained, let's move on to CMAS, an optimizer that uses covariant metrics. For context, MesoNet was entirely built with Keras and Adam as its optimizer. Also, my implementation of both CMAES and PSO use Meso-Inception-4 as the base model. CMAES which stands for Covariance Matrix Adaptation Evolution Strategy, is an optimizer that evolved, pun intended, from the concept of evolution strategies, which, as you could probably guess, is based on the ideas of evolution. It is state of the art in the evolutionary computation field and has been adopted by many as a standard tool for continuous computation. The main idea of CMAES uses a combination of a covariance matrix and the model's initial weights to find a new optimal solution from a multivariate normal distribution. These solutions go through a loss function to be evaluated, which in the case of my implementation is a mean squared error loss function. CMAES has many features, most prominently these ones. Starting from the top left, we have robustness. CMAES is pretty good at dealing with noise and local optima, and it does not require any calculations of the gradient to do its job, meaning that it is derivative free. However, the disadvantages that it has is the computational cost. When presented with a model with large numbers of parameters, CMAES might reach a high computational cost. To prevent that, the parameters need to be tuned optimally, which could get difficult. On the next slide, we have my implementation of CMAES. As CMAES isn't available by default in Keras, I needed to initialize a custom optimizer class. Some methods needed to be overridden, such as getUpdates and getConfig, as the methods CMAES needs are logically different from the ones in Keras. Update step is a case of being needed by Keras, but not being used to do anything as the weight updates are handled by getUpdates above. Now, for the results. We have a whopping 58 seconds of runtime with an average of 9.2 out of 12.7 gigabytes of system RAM for the training process, using a total of 600 images, 300 fake, 300 real, alongside 10 epochs. Now, I would really like to show the accuracy of the model trained using this optimizer and see how it changes. But unfortunately, Google has had enough of me doing my assignment and decided that I shouldn't be allowed access to the runtime. But no matter, the runtime is what's important here. The next optimizer in queue is PSO, an optimizer that was inspired by the birds and the fishes. PSO, which stands for Particle Swarm Optimizer, is an optimizer that simulates the movement and interaction of a number of particles in the search space. Each particle in the given space has a position and velocity tied to it, and both values get updated with each iteration of the model. Updates are reliant on two things: the particle's personal best and the global best. This allows for a certain form of stochastic behavior among the particles, while learning from its own experience and the particle swarm's experience. PSO is straightforward to implement and easy to understand, a very big difference between it and most other optimizers. In comparison to CMAES, it has much fewer parameters that can be tuned. However, the cons are the parameters are much more impactful with just a minute change. The particles might even converge much too quickly with unsuitable parameters, resulting in a suboptimal solution being produced. With all that said, let's take a closer look at PSO's implementation, namely my implementation of PSO. I defined a separate training method as PSO's objective function is logically different from what's provided by Keras. But with all these blocks of code, my implementation of PSO is incorrect, and as such, I can't be sure about the performance of PSO against CMAES and Adam. And the results are three question marks. The unknown, unfathomable, mysterious Schrodinger's PSO results, if he implemented it correctly. Thing is, I can't even work on the PSO implementation as once again, my Google Colab has run out of the free tier GPU usage. If only I could have some form of support from the renowned institution of highest education, Monash University. But alas, I digress. Now, Here is the demo section. Allow me to open my collab. So as you can see, this is my collab. Name, Tay Chean Hao, student ID, and my title over here, and a bunch of code. But when I try to connect to the runtime, yeah, I cannot connect to the GPU backend because of usage limits in collab. So very unfortunate, but I won't be able to show a demo today. Back to the presentation, the slides. In conclusion, I have tried to implement both CMAES and PSO, but much like the most popular book of all time, Adam plays quite an irreplaceable role. CMAES might be able to perform better with proper parameter tuning, but the high computational cost is quite discouraging. In the case of PSO, as it works the best with low complexity algorithms, PSO might not be the best choice when it comes to meso inception for. In the end, it's probably the best to design your model with a specific optimizer in mind, especially when computational cost is one of your priorities. Thank you.